So this is a research about how to take a shape, exaggerate its features, and make it look like a caricature of itself. My name is Matan Sela. This is a joint work with Yonathan Aflalo under the supervision of Professor Kimmel. So what exactly is a caricature? Well, according to the definition, it's a drawing that overemphasizes unique feature of a subject. Here you can see Bill Clinton, for example, and here's caricature, in which some features are exaggerated. Now, drawing a professional caricature is artistic skill that require long practice and some talent. Usually, the process an artist goes through in his mind works as follows. First, the artist takes a facial image of a subject, then extracts key characteristic line of the subject and compare it against some average model in order to detect several differences between the two. For example, if we look at the distance between the nose and the upper lip on Bruce Willis' face, we might notice that it is larger than the average distance. Then the artist draws a sketch in which these differences are even exaggerated, as you can see here. Later, the artist paints his sketch according to the original image. Now, clearly, for different artists might create caricature of the same subject that are different from one another. The objective of our algorithm, of our research, was to develop a controllable framework that enables us to take any three-dimensional shape and to create a caricature out of it. And by controllable, I mean that we can control the amount of the exaggeration we have in our algorithm. In addition to that, we require our algorithm to preserve isometries. What does that mean? It means that if we take two instances of the same subject in two different positions, as you can see here on the left, we put both of them into our algorithm. What would like to happen is that we get two instances of the same caricature at the output, as you can see on the right. Why would we like such a property? Because then we can animate our sequence of pseudo-isometric shapes, as you can see here on the right, and get an animated sequence of our caricature, as you can see here on the left. Now, there are other works in the field. Usually, they can split into two schools of thoughts. The first one is the model-based approach, in which we try to exaggerate features with respect to some reference model. This is an approach that tries to imitate the process an artist goes through in his mind. One of the earliest work in the field was done by Brennan. She developed a software for exaggerating features of facial images, and the user was needed to extract first the sketch of a face by clicking on points on the facial image. And then the software found a point-wise correspondence between the sketch and an average face. Then the user could control the distance between each point on the sketch and the corresponding point on the average one. And here is one of the results. We can assume that this person might probably have longer head than an average one. Some generalization of this approach was developed by Vetter and Blantz in '99 in a remarkable research. They developed a PCA model for three-dimensional shapes, both for the geometry of faces and for the texture of them. So they represented each face in some high-dimensional space, space of coefficients. Let's think of each point here as a representation of a face. For example, let's think of this face represented by this point. In order to create caricature of this subject, they looked at the line that connects between the representation of a subject and the average representation that is marked here in a red X. And they reconstructed a representation that is on the line but far away from the average. And here is one of the results. The other school of thought for exaggeration is a geometry-based approach in which the exaggeration is done without any model to refer against. That means that we exaggerate the features based on the geometry itself. So one of the earliest work in the field was done in our group by Steiner, Kimmel, and Freddy Brookstein. What they did is to develop a framework for exaggerating features of planar shapes. What they did is run the curvature flow on planar curves, but instead of going forward in time, they ran it backward in time in order to exaggerate the features. Here, for example, you see the initial curve, and after several iterations, they found a stable way to run the curvature flow backward in time for a short time step, and here's the exaggerated features. Another approach in the field was done by Chuang and Kashdan. They developed a framework for exaggerating features of three-dimensional shapes that is based on the solution of the screen Poisson equation. Now, the screen Poisson equation is an equation that is the Euler-Lagrange equation of a functional that enables balancing between a preservation term or a fidelity term that tries to preserve the values of functions on the surface. And the other term was exaggeration term or smoothing term that enables the user to exaggerate the shapes. Our approach differs because it preserves isometries, and I will prove it to you. So let's talk about our approach, but first let me explain the deformation technique we used in order to exaggerate features. So let's think of our shape as a surface, which is a two-dimensional object embedded in a three-dimensional world. Each point on the surface can be represented by three coordinates, and we can think of these coordinates as three functions defined on our surface. If we calculate the gradient of these three coordinate functions, we get three different fields that are restricted to the tangent plane at each point on the surface. Now, the gradient-based deformation techniques works in two steps. The first step is to locally transform these three fields. For example, we can rotate them. And the second step is minimizing this functional. This functional tries to find the new coordinate function, x tilde, y tilde, and z tilde, whose gradient is closest to the manipulated field, the field that we manipulated locally. Now, the minimization of this functional is done by solving a Poisson equation, this Poisson equation, for the three different coordinates. Let's see an example. So if we take this straight cylinder and we take the three fields and rotate them by 90 degrees at the top of it, and we don't change the orientations of the gradient fields at the bottom of it, and for each point in the middle, we rotate it between 0 and 90 degrees, according to how far it is from the bottom or the top. And then we solve the Poisson equation, we get this bent cylinder. What we propose for exaggerating features is to scale these gradient fields locally by the Gaussian curvature. Now, the reason why we use the Gaussian curvature is first because it's a feature that tells us how curved the domain is. And in addition to that, it is preserved under isometries, and I will show you later that it allows us to prove that our algorithm preserves isometries. So again, we need to solve this functional in order to find the new coordinate functions. And in order to control the amount of the exaggeration, we scale this gradient field by the absolute Gaussian curvature in the power of gamma. For gamma equals to 0, we get the same source shape. Let's see an example. So if we have this purple lion, and we scale locally these three gradient fields according to the Gaussian curvature, we get this unconnected shape in which on flat domains the shape shrinks, and on the curved domain, the shape stretches. Now, if we solve the Poisson equation, we get this caricature version of the purple line. Now I'm going to prove to you that our algorithm preserves isometries. So if we have two shapes, M1 and M2, suppose we have a parameterization for the first shape, which is denoted as S1. S1 is a map between the UV domain to the shape. Now suppose we have a map between each point on M1 and M2, which is bijective and smooth. Now I'm going to explain what isometry really means. So if we take if we comprise a parameterization for M2 that is comprised of phi applied on S1, and this new parameterization is such that the metric at each point is preserved, then phi is said to be a local isometry. Now the metric is defined as the Jacobian transpose times the Jacobian of the parameterization. One consequence of this definition is that if we take for any pair of points on one shape, if we calculate the geodesic distance between the pair of points, it will be equal to the geodesic distance between the corresponding point on the second surface, if these surfaces are isometric. And phi is the our isometry. Now I'm going to prove to you that if I take two shapes, which are isometric to one another, S1 and S2, we put both of them into our algorithm, and we minimize this functional for both the shapes, and we get this two caricature, S1 tilde and S2 tilde, then if the functional minimization reaches 0, then S1 tilde and S2 tilde are exactly isometric to one another. And here's the proof. So if we reach 0, it means that this integrand is 0. And we can write the Jacobian of the caricatures as locally by the absolute Gaussian curvature times the Jacobian of the surfaces. And if you calculate the metric of the first caricature, by definition, it is equals to the Jacobian transpose times the Jacobian. And if I plug this identity into here, it is equal to the Gaussian curvature squared times the Jacobian transpose times the Jacobian of the original shape. And this is by definition the metric. Now, since S1 and S2 are isometric, for each point, the Gaussian curvature on the first surface and the Gaussian curvature on the second surface are equal. And in addition to that, the metric is equal. And if I plug this into here, I get that it is equal to the second metric, the metric of the second caricature. And that proves that our caricatures are exactly isometric to one another. Now, two limitations of our algorithm is that our surfaces, the surfaces we deal with, must be a manifold. That means that they cannot touch, they cannot touch themselves in one vertex. And in addition to that, each edge needs to be adjacent to not more than two triangles. In addition to that, the shapes we deal with need to have bounded curvature. That means that we cannot apply them directly to depth images. And I will show later how we deal with it. So here is, let's see some results. So here, the color here represents the Gaussian curvature of the source shape. And here is the exaggeration for gamma equals to 0, to quarter, and for gamma equals to half. And you can see that domains with high Gaussian curvature is stretched under the curvature, under the caricaturization. Here is some other example. A lot of people tell me that it's not appropriate to put this person specifically. And one nice application of it is that we can take any subject, create a caricature of him, and print it in a 3D printer since our algorithm doesn't change the topology and doesn't create any holes. Here is another result. Here is another demonstration of the fact that our algorithm preserves isometries. Now, since our algorithm is driven by one parameter, we found a nice application for it, in which this parameter is driven by the sound that is being played. And we could find a way to create a caricature for any subject by taking a depth image of any subject. Here's my advisor, Kimmel, and we used the automatic algorithm for extracting key feature points on face, and based on these points, we match a smooth template, which you can see here on red, to the depth image, which you can see here on blue. And then we could create, here is the result of it. So I showed a controllable feature enhancement model. I proved to you that it preserves isometries, and I showed a nice application which enabled us to create a caricature with respect to some music. Thanks.